Thank you everybody for attending this in-depth session where we'll talk about multiple aspects of coherent optics. Basically, we will start off with a brief overview of the evolution of these optics. We'll explain, of course, why they're needed, why people want them so badly. We'll talk about some technical aspects as well, and we will close off this session with some testing elements associated to coherent optics. So, the presenters for the session today are Steve Jha, Distinguished Technologist at Cable Labs, and myself, Marcos Vasconcelos, Product Line Manager within Expo's Transport and Datacom Business Unit. And with that, I pass the floor to Steve. Many thanks for joining us today, Steve. And you have the floor to kick off the show.
Thank you. Thank you, Marcos. Good morning or good afternoon, depending where you are, everyone. Thank you for joining this Expo test talks today. I would like to take this opportunity to thank the Expo team for inviting me to speak today. I'm delighted to be here and give you a talk on the coherent optics technology evolutions. My name is Steve Jha. I'm a distinguished technologist from the Optical Center of Excellence in the wired group at Cable Labs. Let's go to the next slide, please, Marcos. As you know, coherent optics is a game-changer optical fiber transport technology. It has completely transformed optical transmission systems and enables a widespread deployment of DWDM networks to 100G, 200G, and 400G per wavelength. Over the past decade, coherent optics has gone through multiple generations with 2 or 3 year technology transition cycles as shown in this diagram. The first generation is in 2010. They were based on the single carrier polarization division multiplex, the QPSK modulation format, and achieving a spectral efficiency at 2 bit per second per hertz over this conventional 50 GHz optical grade. Therefore, the system capacity in this fiber C-band transmission window is around 10 terabit per second. But today, is 10 years later or 11 years later, we have 400ZR pluggable digital coherent optics, and 800G coherent system are also available based on the 7 nanometer CMOS process with around 1 billion gates in a chip, leading to the capacity now larger than 25 terabit in C-band, or even for the ultra high spectral efficiency, we go 40 and 46 terabit per second. In the whole C-band, if you combine the L band, it's going to be even larger. So the next step would be the 5 or 3 nanometer CMOS process, the DSP engine for the 800G pluggable coherent optical module. The new generation ASIC, every time from the 90 nanometer, 40 nanometer, all the way to the 3 or 5 nanometer in the future, it meaning not only the smaller chip, but lower power consumption and the more powerful performance. So why is coherent optics so special, so attractive? I'm going to let you in on a little secret here. When we do the conventional photo detection, meaning direct detection, the intensity modulation and direct detection, we are just using the amplitude to represent signal, only one dimension. With coherent detection, we use a local laser source as a reference. We can achieve linear conversion of optical field instead of optical power in direct detection. That actually enables the modulation and detection for 4 independent degrees of freedom, 4 dimensions instead of 1 dimension, the amplitude and phase in 2 polarizations, X and Y. With this local oscillator, we can also provide significant so-called coherent gain and do the wavelength selection without the need of optical filter. Coherent system also doesn't have power feeding like in the direct detection. It has more efficient power distribution along the signal occupancy. Then the powerful digital signal processing can equalize the optical impairments for the very high sensitivity of coherent demodulation process, from the front-end correction all the way to the chromatic dispersion, polarization mode dispersion, and then eventually carrier and phase recovery here. So this is the secret to have the very high link margin to enable the higher performance and lower cost implementations. So coherent optics starts in its application, we know, in the long haul, in the regional, and then migrate to the metropolitan area, right? We have pluggable, the CLP, CLP2, ACO, CLP2, DCO. But the current development of ASIC DSP chips and the corresponding the optical modules is moving in two directions. Above this diagram showing here, the first path is to have the programmable and the comprehensive coherent DSP, which is capable of processing data rate from 100G or 200G to the 600G and even 800G per single wavelength, with the support of higher modulation format like the 32 QAM or the 64 QAM, and higher net coding gain, the FEC, forward error correction, FEC, using the best-in-class optical or the electrical components there. And the other part is the bottom part here, coherent moving to the access and edge networks. So we can reduce the power consumption and meeting the size and cost requirements for the access applications. For that application, we're typically dealing with less than 120 or the 80 kilometer distance in the access environment. We're not fighting every 1/10 of dB in the performance, right? We have plenty of link margin to relax the requirements for lowering the cost from the transmitter, from the receiver, all the way to the digital signal processing ASIC. For example, the chromatic dispersion is significantly reduced when you move from the long haul to the access, which is a significant portion of the power consumption in the DSP ASIC. And we also know the scale in the access is so much bigger in the long haul and the metro portion. The next slide, please. So for these two different directions for the coherent optics evolution, I'm going to start with the first direction for the access and edge application path. We take the cable operators network as an example here. In the cable, we traditionally use the analog optics to carry DOCSIS 3.1 or DOCSIS 3.0 RF signals. But recently, we have been evolving to a distributed architecture we call the distributed access architecture, DAA, to overcome some of the challenge of the analog optics space and other advantages that provided by the DAA. We use the digital optics in the form of the intensity modulation and direct detection, as I introduced before. Combined with the remote generation of RF signals, we have remote PHY and remote MAC-PHY in the remote location, the fiber node. We can utilize the DWDM to carry multiple wavelengths over a single fiber. That is 10 GB per second now. But in cable, the situation is we have limited fiber reaching to our fiber node, from the hub to the aggregation node, even for the deeper node. We need a technology that is most efficient to carry this abundant capacity from the hub to the fiber node or backwards, not just for the residential services, but for the enterprise connectivities and wireless backhaul. This is the converged and uniformed platform to provide multiple service. We need a technology that is very efficient and very future-proof. And this technology is coherent optics. And this transition to the coherent optics into the edge networks is happening today. Early on, the cable labs recognized the need of coherent optics in the access and edge networks. Cable labs announced the launch of point-to-point coherent optics project during the 2017 Winter Conference. So 3 years later, in the beginning, we received a very high endorsement from the optical industry and formed this working group. So 3 years later, we developed point-to-point specifications just targeted for the access environment. There are 4 specifications that we have published today, including the architecture, 100G, 5-layer 200G PHY and operation support system interface OSSI in specifications. The spec already include the full duplex coherent optics for the single fiber use case for bidirectional connection. We already conduct 2 successful interoperability events at Cable Labs. For 100G version of specification, we expect the 200G interrupt test within this year. And very recently, we also have the first draft release of the coherent termination device, CTD specification. This is especially for the remote fiber node coherent device to have the layer 2 or layer 3 function to switch different aggregate the signal into the coherent or distribute the signal into the deeper node. The next slide, please. And for the second pass, as I mentioned, one is going to the edge, the other one is going to the high performance one. This very high performance, high data rate transceiver. Now we have this 400ZR and 800G. We know the OIF launched the project several years ago related to the coherent transmission technology 400ZR interoperability. As shown in this upper diagram, 400ZR allow the network operator to consider this switch-to-switch or router-to-router based IP over DWDM architecture for point-to-point DCI, data center interconnection application, for the distance up to 120 kilometers. You know, this is interoperability is the K and open is the K. They're using the concatenated FAC, CFAC, with the soft decision inner hiding code and the hard decision outer staircase code. So the form factor for this high faceplate density is QSLP, DD, and OSLP. It's primarily for the hyperscalers. Meanwhile, the 400ZR Plus is the coherent pluggable optics. It's non-standard extension that broaden the 400ZR application to support a few hundred kilometers long, as well as the metro and the aggregation access. The other side is the 800G pluggable here. You know, we know the 400G deployment is going to ramp up this year, but 800G is already on people's mind in the optical industry at the next necessary step to continue to lower the cost. So for this specification, the OIF announced the launch 800G coherent IA effort last year, November. So there's going to specify the interoperable single lambda 800G coherent line specification at the campus, which is 2 to 10 kilometers distance within the data center campus, and also the amplified link go to the 80 to 120 kilometers for this single span DWDM DCI. They are going to occupy 150 GHz spacing with the target to the 22 watt per module. If you consider 400ZR currently, depending on the configuration, is around the number of the 18 watt. So this double the capacity, but only increase the power by a portion. So that's going to continue to lower the cost and the power per bit. On the other hand, the right corner in this diagram is here, next generation coherent DSP. The people call it the 5th generation. They're going to push the capacity close to the Shannon theoretical limit. This is the line card of chassis-based 800G solution. They're using the best in-class components with the support from the 90 gigabaud and higher transmission signals with this probabilistic constellation shaping PCS format like shown here. Like Sienna and Infinera, there is a few of the leading vendors. They already demonstrated the 800G, showing the distance in the range of 600 and 900 kilometers in the controlled and optimized field trial or the lab experiments. So this is the overall coherent optics evolution from my perspective. With that, I'm going to hand it over to Marcos for the coherent optics testing section.
Thank you very much, Steve. So continuing here in terms of testing, so we're talking about coherent pluggables. We can divide actually in two generations based on the link on the data rate on the optical side. So the first generation, as you can see on the left hand side, it had on the optical side data rates allowing data rates of 100 gig or 200 gig. With different clients, as a matter of fact, we see on the first example 100 gig client and having on the optical side a coherent signal allowing 100 gig, or two 100 gig clients allowing on the line side, on the optical side 200 gig, or a combination of 100 gig and OTO4. Moving on to the second generation, we see with the evolution that on the optical side, what it's capable of doing is allowing 400 gig, as Steve was saying, and on the client side, having different clients. You could have one client that's occupying the full 400 gig, having possibility of allowing two 200 gig clients, four 100 gig clients, or even OTN clients as well. So OTU4 and allowing also OTUCN FlexSol. So this is specifically in terms of pluggables, dividing generations. But what we test is actually on pluggables. What do we want to validate? You've probably seen this slide before from previous presentations that we give. We divide the transceiver validation in 5 different steps, 5 different blocks, starting with the validation of modulation, moving on to qualifying how the signal is and being able to operate or to adjust the signal in terms of on the transmitter side with the pre-emphasis capabilities, or on the receiver side with the RX equalization. Another element that is fundamental in terms of transceiver validation is the verification of how the FEC, the forward error correction algorithm, is working. So extremely important. Moving on to transceiver validation and checking aspects such as power consumption and temperature. These are 2 elements that data centers and operators, they have, can be very worrisome for them. They of course want to have pluggables that consume less power and do not go very high in terms of temperature. And last but not least, the capability of operating on the pluggables. So being able to read and write information on the pluggables, it's something else that it's quite important as far as a complete and comprehensive transceiver validation. So moving on to links, specifically to links, client to client. As a matter of fact, we propose here 3 different scenarios. So the first scenario, in which you have a coherent link between the 2 transponders, and you apply or you position test equipment behind switches and routers representing clients, and then you validate that the transmission or the data path and the transmission goes well. So you can validate the link stability, bit error rates, latency aspects. So that is the first scenario. A second scenario, already using, in this case, 400 gig ZR transceivers. So you already have them directly connected to switches and routers, as Steve said. So you don't need any additional transponder or any additional transport equipment. And you would plug the test elements, the test equipment behind the switches and routers and make the same kind of validation. So the example here is again with an Ethernet BERT validation to validate the link stability, the bit error rate, and latency. So that is those are aspects that it would be able to do. And on the third row of the diagram here is you go beyond link validation. You go beyond latency, or you can actually validate the QoS of different services, different streams at the same time. So that is another level of verification in terms of client to client. It's very important and to do. So that was in terms of client to client, but there is another element that you could be testing to maybe segment your whole validation or deployment is the testing between client and line. So you can have test elements that are placed, let's say, on the client side of a muxponder or transponder and emulating their 100 gig signals or 400 gig Ethernet signals. So on the client side, and on the line side, you would be able also to plug or to connect a test equipment using a ZR transceiver or ZR plus transceiver on the line side to make sure that everything is working well, the connection from the line side and the client side and the line side perspective, everything is working well in that sense. So with that being said, those were the slides that we had put together for a presentation today. And I would like to ask Steve if you have received questions on chat box that we can try to clarify or give additional information to you.
Just from the previous session, we have a couple questions, very, very important and very good questions. We start from there.
Please.
So one is, what are the key elements when validating the ZR transceivers? So this is, Marcos, is for you.
Okay, thank you very much, Steve. Yes, so validating transceivers, regardless ZR, NRZ, it doesn't really, or PAM4, it doesn't really matter. So elements that you always want to validate. First of all, especially when you're talking about coherent transceivers, you want to definitely validate how the FEC is acting, the forward error correction, how things are on that in that area. You want to monitor, not only validate, well, you want to validate and monitor the temperature and the power consumption. Those are elements that, especially in data centers, everywhere in the industry, but especially data centers, it's something that is very, very valuable because they have multiple racks, you know, millions of, well, thousands of racks and pluggables, and the temperature controlling the whole environment and the power consumption there, it is extremely important. So those are elements that you want to validate. Checking in terms of bit error rate, doing a quick validation that in terms of the overall performance of the transceiver, everything is okay. So we recommend also a bit error quick validation to check that everything is stable, and you don't, if you install the transceiver on your network element and you start seeing issues, you want to at least be sure that for the transceiver itself, everything's okay, so that if you have troubles, you can already put aside or be how can I say, sure that on the transceiver side everything's clean and clear, and the investigation, if you have troubles, the investigation would go at another level. So just making sure that you cover all your elements.
Great, thank you. And the other question I think is worth highlighting from the audience is that the timeline for the 400ZR. 400ZR is currently really hot topic in the whole optical industry. So we know for the specification perspective is the OIF released the IA implementation agreement version 1.0 at the Q2 2020, this last year. And the product perspective, the general availability of 400ZR product from all the key vendors is, we're talking about the vendors for the module vendor and the DSP. DSP already there from the Acacia, Sienna, Inphi, NEL, or Nokia. So we have the module vendors, small vendors involved for the module development. We have Sienna, we have Fujitsu, InnoLight, Inphi, and any others, New Photonics and Molex. So these key vendors typically can have this GA of the 400ZR is Q1 to Q3 this year. So this 2021, we have the product, and we expect the deployment for the hyperscalers will start from the Q4 this year, right? So after the operators finish up the lab testing and the field trial, we heard several topics on this deployment is going to ramp up from end of this year and early next year. So this is the 400ZR deployment timeline.
So thank you very much for attending this session. Thank you, Steve. It was a pleasure to share this 2 sessions with you, and we look forward to seeing you again next week.
Great. Thank you everyone. Thank you, Marcus. Thank you, Expo, for this excellent text talk.